So we're going to start talking about evaluating limits as x approaches a constant, and we're going to be doing this in two ways initially, and we'll do a little bit of both probably in this video. So one is going to be using a graphical technique and the other is going to be using a numerical technique. So first I want to start with what is not to be confused with the formal definition of a limit. That's later in section 1.6. Here we're just going to talk about the practical interpretation of what it is we're trying to find. So first of all, the limit question itself. So it is a notation that we're going to need to be familiar with. And it is this limit as x approaches c of f of x. Or some people might say the limit of f of x as x approaches c. So either way there. So what we're really looking for, and kind of every word chosen here is chosen really specifically. So first of all, a limit, think about a limiting value. Anytime we're going to be looking for, it's like I've reached my credit limit. A limit is a number, it's a limiting value. So we're talking about, first of all, what real number. So let's start with that notion. What real number? And we're looking for what real number is this function approaching. So what real number is this function approaching? So this function, what limit is this, what real number is this function approaching? So this function here then is the f of x, which means we're really going to be focusing on, I'm just going to kind of say it this way, the y's, the output values. So what real number are the function values, the y's approaching? Again, pretty key here. So we're not actually talking about what it's equal to. We're talking about what it is approaching. So that's key language here with the limit. Okay, so what real number are the y's or the y values approaching as the x's? And so now we're talking about as our x's here. So we're looking at as the x values or the x's. So as the x's here are approaching, erase that just for a second here, rewrite that. So as the x's approach, and so that's kind of the arrow that's saying as the x's are approaching here. So as the x's are, there's my arrow, as the x's are approaching, and then it's as the x's are approaching this number c. So this is the constant c. So as the x's are approaching c, and another key part of this question, so I feel like I'm highlighting everything here because it's all so important, but as we are approaching c from both sides. So let's take a look at this first little graph here, and let's see if we can get an understanding of what might be happening here. All right, so as we look at this graph, we want to look at what are the x's approaching, and in this case, the x's are approaching c from both sides, and then we're going to answer what are the y's approaching. So every time we do this, we need to be looking at this from both sides. So we're going to be looking at it maybe coming in from the left with, let's say, this little purple color. So this is as the x's are getting closer and closer to c from the left. And here we've just sort of zoomed in that little box region there. So as the x's get closer and closer to c from the left, and at the same time, we're looking at as the x's are getting closer and closer to c from the right. So as we're traveling along this function, getting closer and closer to c from the right-hand side. So again, you're really thinking about sort of traveling along the function, getting closer and closer to c from both sides. So getting closer and closer to c from the left and getting closer and closer to c from the right. Now here's the thing. It may be that that point exists right there at f of c with kind of nice, smooth, well-behaved functions. It will. But what we'll find out then is that, in those situations, it might just be that point. But the limit question doesn't really care if that point is there or not. So in this case, as I'm getting closer and closer to C from both sides, it looks like this is actually just approaching, the y's are approaching that function value, like f of C. It's defined and that's what it's approaching. But it's kind of like, a lot of times in class I'll visualize it and show it like with an electric shock. Like if my fingers can get closer and closer and closer to each other, and I almost get to that point, like my fingers might never touch, but if I can get close to that point where I might be able to get a little electric shock, that's the limit. I don't ever actually have to touch. They don't have to actually reach each other, but we get to that point where there might be enough to make that little electric shock that's happening. Okay, so the notation for this. So the limit as x is approaching C from the left gets denoted with this little minus sign right there, kind of in the location where you might see an exponent. So this right here, this is in words saying this is the limit as x, of course, is approaching C, but it is saying just from the one side. So this is saying from the left. And then when you see that little plus sign there, that is actually saying we are looking at, again, this is our limit as x approaches C, but the key here is we're looking at it just coming from the right. All right, so that's our notation for one-sided limits. And so here's what we're really saying, kind of put into a theorem taken right from your book here. So the limit of a function as x approaches C, it's going to exist if and only if both sides of that limit are equal, and they have to be coming into the same value. They have to be coming into that L. So this value of L, this limit that we're talking about right here, so this value of L that we are getting closer and closer to, that's really our answer. So this is the answer for the limit. So this is our value of L here. And it may or may not actually be a point on the function. There could be a little hole there like we're going to see in this next example. So let's look at a graphical example here to sort of develop this concept. And what I'd like to do in each of these, I'm going to actually make each of these parts are going to be like a part A on these. So what I want us to think about, at least on the first few, these are going to be part A. And then what I want for part B is I want us to contrast this with what I'm going to call kind of the good old pre-calculus question, which is just what's f of that function? Because I want us to really focus in on the difference in these two questions. The question you might have been asked before calculus, and then the question you're being asked now in this calculus course. All right, so let's take a look here. So our first example, it says, what is the limit as x approaches 3 of f of x? And then also, what is just f of 3? So first, let's actually do part B. Let's just do f of 3. So f of 3 just says go to where x equals 3, go to that function, and look, oh yeah, it looks like f of 3 is defined, and f of 3 is equal to 1. Now, the limit question, though, is something very different. So the limit is saying, what are my x value, as my x values are approaching 3 from both the right, and as my x values are approaching 3 from the left, what are my y values approaching? Well, here, it just so happens, looks like, those are also approaching 1. So sometimes, like in the opening graph I have, sometimes they may be the same. In nice parts of the graph where, it's continuous, and we may have the point exist right where the limit exists. But that is not always going to be the case. So let's look at number 2, f of 4. So if I went to 4 on this function, there's a big open circle there, and there's no point anywhere else. So back in your college algebra pre-calc days, you would have said, oh, well, that means that f of 4 does not exist. But again, If I was to ask you the limit question, the limit as x approaches 4 requires that I look at what happens as I get closer and closer to 4 from both sides. So as we travel along this function and we get closer and closer to 4 from both sides, I can get infinitesimally close there and I could, boom, generate that little electric shock, right? Like I never actually touch, but I'm getting infinitesimally closer to this value at 2. In this case, the y value, the output value I'm getting closer and closer to is 2. So that's the limit. It's the point you're getting closer and closer and closer to. It's the y value of that, even though you may never actually equal that y value. All right, let's look at the same thing here at f of 1. So f of 1, the good old pre-calc question, where is the point defined, if anywhere? Oh yeah, no, this point's defined. There's a big dot up there at 2, so f of 1 is equal to 2. But once again, the limit question is something very different. So as I am getting closer and closer, this time to 1 from the right, and as I get closer and closer and closer to 1 from the left, looks like my y values are getting infinitesimally closer. I'm going to generate that little electric shock between my fingers. At the y value I'm approaching, I'm getting closer and closer and closer to 1. So that is my limit. So as you look at these first few examples, you start to see like, wow, all bets are off when it comes to the relationship between whether or not the point exists and whether or not the limit exists. They are two completely different questions. All right, so this next one, it looks like we're being asked, and you may be asked just for like a one-sided limit. So if they only ask you for one side or the other, like in this number 4, just what is the limit as x approaches 2 from the left, I'm traveling along my function, getting closer and closer to 2 from the left, and my y values here are simply getting closer and closer to 2. So coming from the left, I'm getting closer and closer to 2. The limit as x approaches 2 from the right, so as I travel along my function, getting closer and closer to 2 from the right-hand side, these y values are getting closer and closer and closer. Remember, I don't care if they actually ever reach the point, but they're getting infinitesimally closer to 3. So the limit as x approaches 2 from the right is getting closer and closer to 3. But the overall limit then, if we were asked about the overall limit, we would of course have to say that this overall limit does not exist because, and this is the heart of what we've been working with, because the limit as x approaches 2 from the left of f of x is not equal to the limit as x approaches 2 from the right on this function f of x. Because coming from the left, the limit's going to 2. Coming from the right, the limit's coming to 3. And as I'm coming into different values there, I'm never going to generate that little electric shock. Like my fingers aren't going to get infinitesimally close to each other. They're coming into different values. There's this big gap. There's this jump. And in those situations, the limit is not going to exist there. Okay, so this is the first way we're going to talk about limits, is going to be to talk about them graphically. So next time we'll come back and we'll look at an example of determining the limits numerically.